Welcome to Spring LIB.
This question first asks you to review some content found in previous chapters, namely the concept of Lewis structures. It describes the compound chlorine dioxide as being a common commercial bleaching agent. It wants you to draw the Lewis structure first for ClO2. When you draw the Lewis structure for ClO2, you'll notice something unique. Chlorine has 7 valence electrons, oxygen has 6, there are 2 of them, so we have a total of 19 valence electrons available, an odd number of valence electrons. This is unique. When we draw the Lewis structure, you'll find out that chlorine in the middle does not have an octet. It only has 7 valence electrons surrounding it, because that's all that we have. That's all that's available. We could have a double bond formed that would then give chlorine 9 valence electrons, which is also a plausible Lewis structure. However, either way, it's going to have an unpaired electron. This is then the answer to part B. Why would this want to be reduced so readily? Well, as you recall, electrons like to be paired, so it doesn't matter whether there's 7 or 9 valence electrons around chlorine. It can readily accept another electron so that all of its electrons are paired. For part D, it says that when it's reduced, it produces the chlorite anion, ClO2, and then wants you to draw the Lewis structure for ClO2 minus. There are 7 valence electrons from chlorine, 6 from oxygen, there are 2 of them, plus the 1 electron that it acquired to become an anion. This now gives us an even number of valence electrons, 20. So in drawing the Lewis structure, we do now have 8 valence electrons surrounding chlorine, and we'll put it in brackets and put the charge outside because it is an anion. Next, it wants you to determine what the bond angle is for OClO. Well, you'll notice there are 4 electron groups surrounding chlorine. With 4 electron groups, this has a tetrahedral electron group geometry. A tetrahedral electron group geometry has bond angles of 109.5 degrees. However, with 2 lone pairs, pushing down on that bond angle, because lone pairs occupy more space than bonded pairs, we will end up with a bond angle that is something just under 109.5 degrees. Next, we have a limiting reactant calculation. You were given amounts for chlorine and for sodium chlorite, and you're asked to calculate the amount of chlorine dioxide that can be produced. As you recall, for a limiting reactant calculation, it's easiest to calculate the amount of product you can make with each reactant, and the reactant that produces the least amount of product is the limiting reactant, and that least amount of product will be the amount of product that can actually be produced. So one of the reactants is sodium chlorite. We have 15 grams of it. If we divide that by the molar mass of sodium chlorite, we'll get the moles of sodium chlorite. Then looking at the stoichiometry of the balanced reaction, 2 moles of it will produce 2 moles of our desired product, chlorine dioxide. Knowing the moles of chlorine dioxide, we simply need to multiply that by the molar mass of chlorine dioxide to calculate the mass of chlorine dioxide that could be produced from 15 grams of sodium chlorite. And we get 11.19 grams. But this isn't necessarily the answer, because we need to figure out how much we can make with the other reactant. The other reactant is chlorine gas. We have 2 liters of chlorine gas available at a pressure of 1.5 atmospheres and 21 degrees Celsius. So using the ideal gas law, we can calculate the moles of chlorine gas available to us. Moles will be equal to PV divided by RT. The pressure is 1.5 atmospheres. The volume is 2 liters. We divide by R, 0.08206, multiplied by the temperature, which is 21 degrees Celsius plus 273 to get it into Kelvin. And we get 0.1243 moles of chlorine gas that are available to us. Now to calculate the mass of chlorine dioxide that can be created from this many moles of chlorine. We'll we'll multiply this by the molar mass of, no molar mass required, we're already in units of moles, so we'll go straight to stoichiometry. 1 mole of Cl2 produces 2 moles of ClO2. Then when we have moles of ClO2, we'll multiply that by the molar mass of ClO2 to get the grams of ClO2 that can be produced from this many moles of chlorine gas. And we get 16.77 grams ClO2. This is more than what can be created from the 15 grams of sodium chlorite. Therefore, this smaller amount, 11.19 grams, will be the mass of the product that will be created, and our sodium chlorite ends up being the limiting reactant.